Hi everyone, welcome to another video of CS202 Online. Today we're going to be looking at a topic that is known as recursion. And first of all, actually, let me stop and congratulate you. If you got to this video, it means that you've actually learned all the C++ content for 202. Yeah, that's it. From now on till the end of the semester, we're not learning any new C++ content. We're actually done with that. Now, does that mean that you've learned everything there is to know about C++? Not quite. In fact, there's a lot of things that are covered in 135 and 202. But what you do know so far is the basics enough to get you where you need to be for future classes like 302. And more importantly, you know enough that you can seek the rest of the knowledge on your own time by yourself as you need it and succeed at that. And that's a big part of being a programmer, is not just to be able to watch a video and repeat what someone's doing, but to be able to kind of go beyond that and to be self-learning and independent and self-sufficient, in the sense that if somebody tells you to do something and you don't know how to do it, you can seek out and learn how to do it. And that's just, by the way, not something for programming, but something that you should be good at in life in general, because you're never going to get all the answers, on your lectures, on your classes. You're always going to have to kind of seek beyond that, whether that be because you don't understand what the instructor is saying, or just because it's just not something that there's enough time. I mean, there's really like an infinite amount of knowledge out there and only a limited amount of time that you have. So no matter what you do, you're never going to learn it all, which is okay. You just learn what you need and you keep it lean so that you don't get overwhelmed. And so that's kind of what we're at. We learn templates, we learn operator overloading, we learn object-oriented programming, which is a concept actually, but there's a lot of things behind that concept that we have to learn, such as inheritance and virtual functions, and even like something as basic as function overloading is technically a concept more than programming, right? So we're already kind of used to this idea of learning more than just like, this is how you code, this is the syntax, this is what you do, right? We're beyond that. Even so far, but now we're going to go even further, because we're not going to learn any more tools. There's no new syntax you're going to learn from now on in 202 or 302. Really now it's all about learning concepts, and so we're going to start that today by talking about this with recursion, which is a concept. It's not a programming. It's not programming. There's no code that you're going to write that's special for recursion. There's no special keywords or syntax that you have to do for recursion. It's just a concept. And after recursion, we're going to be looking at a data structure known as a linked list. And that's going to be basically pretty much the rest of the semester, although we will probably look at stacks and queues at the end, but not as in detail as linked list. And that's also a teaser for 302, which is the data structures class. As the name implies, data structures is all about what 302 is, and linked list is a data structure. So you get like a tease of that in this class. And data structures are really important. Obviously, I don't want to go into a monologue about why that's the case, but you're more than welcome to look ahead and look at some of my 302 videos, or just wait until you take 302 to know why there's such a big deal. But for now, you are going to get a tease of that as you learn linked list. And again, linked list is not some special C++ thing. It's a concept that you're going to learn. And you can do a linked list in many different programming languages, by the way. Just like you can do recursion in many different programming languages. They're concepts now, okay? So just want to warn you about that. That doesn't necessarily mean the class is going to get harder or easier. It's just learning something else. And it's good because, like I said at the beginning of this video, congratulations. You learn all the basics now of C++. You can go out and code whatever you want now. Your imagination is the limit, and maybe your amount of RAM. So be proud of that. And, now we can start looking at cooler things than just learning how to program. So, recursion. Normally, how I do the recursion lecture is I just tell you what recursion is, the basics of it, and then give you examples. But I thought I would try a little bit differently today. And you're more than welcome again to watch those videos too, to get more examples and just more knowledge. But I want to try it a different way. I want to bring up recursion as a solution rather than giving it to you as a tool. So let's think about the basics of doing something as 135 level, as obvious as repetition. Okay? So if I told you right now, and yes, even though we're talking concepts, we are going to limit ourselves to talking about C++ and things like that, because I'm not going to just randomly switch into Python or something, as much as I would love to do that. Okay? So we're still C++ land. It's just now we can use C++ as a tool to show you concepts like recursion. So if I told you right now, I would like you to write a program that infinitely prints the number 1 to the screen. What would you do? Well, you would use a loop, right? That's what you learned in 1 through 5. That's what you've been doing so far, is you would use a loop. Now, what kind of loop would you use? There's a lot of different ones you can use. Well, not a lot, but there's the 2 main loops that you can use, and I guess a third option, right? So one way you could do it is just to use a while loop, right? So I could say something like while true, just so that it always runs, and then do whatever I want to repeat. So in this case, I just want to print out a 1 to the screen forever. I guess I could add an end line and just put a 1 after each line, but I'll just do cout like that. Okay, so this piece of code could be anywhere in main or whatever. That's irrelevant. The point is that this piece of code that you have here is a loop, and this loop is going to run forever. If I were to run this, in theory, it's going to run for infinity, right? In practice, it won't, because you could run out of power. Like, the computer could, like, I don't know, eventually like wear out and shut down. So I'm not saying this computer can really run forever, but in theory, assuming a perfect system that could actually be on uptime for a long time, you could be spamming the terminal for infinity and beyond, right? Cool. Okay, so what if I said, hey, I'm sorry, but I'm taking while loops away from your programming language. Do the same code. What would you do? Well, if all I said is you're taking while loops away, one thing you could do is you could use a for loop, right? So I could say something like this. Doesn't really matter what's in there, so I can just leave it empty so that it always iterates forever. And then just do the same thing, right? And both of these pieces of code are going to just iterate forever with a 1. Okay, now I'm still using the same keyword here, iteration or looping, right? This code is just going in circles forever. And if I do the other option, which is a do while loop, which we don't usually use, but I could put it in here, then I could also go ahead and do this same infinite printing of 1. But what if I said, hey, when I said I'm removing loops, I actually meant it. No more loops, not any kind, whether it's a while, a for, or a do while, or using some fancy go-to statement, which we don't really teach, by the way. That's one C++ thing we don't really teach if you think about it in 135 or 2, go-to statements. Reason being is because they're kind of messy. We don't want to encourage you messy behavior. But go read on them on your own. It's not like knowledge is forbidden. It just makes you kind of messy of a coder if you learn them too early on in your career. But they all have a place in programming. That's why they still exist. So, labels and go-to statements. So yes, you could do it with that, but it's still basically a loop. However, I want to show you another way that you could do this that maybe is not so obvious, particularly if you don't know the topic of today. And it involves the usage of functions. So let's go ahead and write a function. And this function is not going to have any parameters, no return, so void. And for now, let's just put a cout. Okay, so if I said, hey, this is a solution to what you asked, another way of writing this, I would say you're wrong. Because this function, if I call it somewhere else in main or whatever, so it actually runs, because just writing the code is not going to make it run, right? The function is just there, but you're not executing any code until you actually make a function call, right? So somewhere in your code, little blink there. So somewhere in your code, you have the foo, and it calls a function, and it runs, and it prints a glorious number of ones. So it's not really working, right? Obviously. I mean, you kind of expected it at this point. You've written tons of functions by now. So is this really another way of doing it? Well, I wasn't done yet. I just wanted to start with this and then add the little, there's the rug kind of thing, as the bar would tell us. Could I modify this code to kind of mimic the idea of this infinite one? Well, everything you need is here already. What do I need to do to make this code run forever? By that I'm saying to make the ones be printed forever, because that's the original goal. Sure, I could put the foo in a while loop, right? But that's kind of like it's like kind of like a loophole to my requirement. Pun intended, I guess. No, I don't want to use loops, so I'm not going to do that. But we're in the right direction. We know that calling foo makes the code run once. We need a way of calling foo repeatedly that won't stop without a loop. So what do? Like I said, the answer you seek is here already. That answer is in the form of a function call. Right now, take this function call and put it inside of the function itself. Like that. Now you might be thinking like, whoa, this is blasphemous or something. Hold on. You might have never tried this, but that doesn't mean it's not going to work. Let's look at and kind of see what exactly is happening. The first time the code runs, somewhere in here we have our foo call, right? So we still have this foo call here. Once that code runs, we see our cout statement, right? So it printed out once. And then, look at that, there's a foo call. So what's going to happen then? Well, this code execution is going to stop and it's going to make a new instance of foo, right? So if I pretend this is my terminal, I have a 1 printed out from the first time it ran. And when I see this foo function call, this piece of code stops. And then a brand new foo instance is created and executed. That brand new instance runs the cout line. And so we get our second one. But guess what happens after that? It sees the foo function call. So what happens then? This instance of foo stops and a brand new one, a third one, is created. And you run that code, which also gives you a 1 and also has another foo function call. See what's happening? Do you see how this is going to be running forever? In theory, at least? Yeah. So this might look kind of ghetto or like weird to you, but this is definitely a way of infinitely printing, in theory at least, once, right? This is recursion. This idea, this crazy idea of putting this function call inside the function itself to make it run, by itself. That's recursion. Okay? Now, I don't expect you to all of a sudden turn around and say, like, hey, I'm a recursion expert now. That's why we're going to spend on this a week. But it's a start. So, let's just really make sure you understand this code right here. Okay? And for that, I would like to direct your attention to something known as the call stack. Okay? So we already know memory has a heap and a stack and a heap, like to different parts of memory being stored. But code itself, when it's being executed, is also stored in memory. And so that part of memory that controls the execution is typically called the call stack. And why is this useful? Okay, let's just forget about this foo function for a little bit and make a brand new piece of code. And I promise you there's not going to be any weird calling yet. Okay, so this brand new piece of code we're going to write, it's just going to have a couple of functions. I said no foo, so I got to do something other than foo. So we'll do fee. And then maybe I'll do one more function. This one will make valid returning, why not? We'll call this one car. Okay, and you know, it doesn't really matter what's in here for now, so I'm just going to pretend these dots represent some code. Let's make one more function though. Call this one bus. Let's add a parameter on that one. Okay, maybe there's a semicolon at the end of all that code. So we got all these functions, and now I am going to go ahead and write some code in main, which is a function itself, by the way. And in here, I'm going to call car. I'm going to call bus, pass a parameter, and then fee and bar. Maybe I'll call fee twice. Or maybe I won't call bar right now. Sure. Okay. So if this is my piece of code, oh, and maybe let's add a one variable up here, like an int z get 5. Okay, I like that because like the 2 and the z and the 5 look like mirrored. That's kind of like trippy. Yeah. Okay, going back to serious mode. All right, so the way the call stack works when your code starts running, you can think of that like a little vertical line. Okay, and have your main here. And there's a couple of information that has to be stored there, and that is going to be your local variables, right? So this actually is very relevant to talking about scope. So if you're still iffy about scope, maybe this will help you out. But yeah, so your main function right now has one variable. Well, technically it has a couple extra variables because it has like argb and argc, but forget about that. It just has one variable, which is the z, okay? So you can think of like here being a z and a 5. Okay, well, technically to think of it more like a box that contains a 5, and that box is called a z. Okay, so when your code is running and it sees the function called fee or 5, I don't know how would you pronounce that. I guess 5. I don't know. Okay, but yeah, when it sees the function called to fee or 5. Execution stops, right? Your code execution stops right here. And it saves this context and creates a new one. And that new one is the file context. In fact, in the code itself, there's a little pointer arrow that points to the new context. And that's done so that your program needs to remember, right? Because like imagine that you're looking at this code on the right here or left, and you go through this code, and when you come back, you're like, which file did I come from? This one or this one? Like you need to remember where you came from. That's not trivial. Like you gotta know, so you gotta store a piece of information that remembers where in the code you were. It's not enough to be like, yeah, well, I just came back from 5, so I'm just gonna look for a 5 function call. Yeah, but there's 2 of them, right? So like, which one did you come from? So you gotta remember this. Okay, when you take 219, you're going to go very much into detail with this awesome stuff, and even further when you take 370. So for now, we're kind of just glimpsing over it. But yeah, that information is kept here in the call stack and the context, okay? And so this is useful because when it comes to scoping, like right now, you know, phi has nothing, but like let's say that we add a variable in there, there's an x in there. This phi is going to create this x variable that's going to live here, right? And when this phi finishes, it goes back to main and it gets kind of removed from the stack, including the contents of the x, right? That's why, you know, every time the function gets called, you get a new instance of the local variables and so on. But anyways, once the phi finishes, like I said, this goes away. And you're running more code in main, and then you get to this function, and the same thing happens. You get a car here. This context stops. It remembers that it came from there. It does the code from car in the local variables, and it comes back, right? So what if we have a function call inside another function? So let's say the bus function has a function call to bar. So somewhere in here, there's a bar along that code. Okay, well, we did the car one. We come back to main. We see the bus. Hello, bus. We start that code, so we add a new context for bus. This context, by the way, has a parameter, right? So technically here, you know, it's going, whatever we give it a name, yeah, A is going to contain a 1, right? And then any local variables that might also appear here, right? As you're running that code, you're eventually going to see the function call to bar that's inside a bus. At that point, execution stops here. It has to remember that it stopped here. So there's another arrow here amongst the different codes. So like, let me expand bus so you can see that. So bus actually has some code here. Maybe amongst this code there's a variable. Let's do a V. You got the bar, you got some more code, and then the end of the function, okay? So as you're running this, there is a V in here, and it contains some data, whatever that might be. And you're running some code, and eventually you see the function call to bar. So that context is going to have to be saved, and that pointer, remembering where that function call happened, is going to be remembered. And it's going to make a new one. So now we have the main one to bar, and then we have a bar one, or sorry, the main to bus, and then bus to bar. Okay? Now bar itself is just some code. It's just going to run, no function calls. It's just going to run this code. When it finishes, then it'll follow back the arrows, backwards per se, and just kind of go back up here, right? And then it's going to get erased from the stack. Well, technically speaking, it's like memory allocation. It gets deallocated, so it doesn't have to like actually erase the content. It just declares it as empty. So then it just gets overwritten next time that something goes over it, right? So we know that. To make it easy to understand, we just think of it like being erased. So yeah, okay. And then we're back in bus. Now we're going to run the rest of bus code. And when it finishes, then we're done with that. Then again, the context goes back down to main. Okay? And then we can go on, we see feed, we go into that, we come back, and we're done with main, and we're done. And once everything's done, the whole stack is free, basically. Okay? Again, technically the content is still there. It's just going to get overwritten at some point. It's the same concept with pointers and dynamic memory allocation. Okay. So why did I go over that? Well, the reason I went over that is because I want to make sure that we're on the same page of like why this is running forever. So let's go ahead and do a call stack for foo. Let's do it over here where the output would have been. So when you see the foo, as it's running the foo code, it sees another foo function call, right? So that execution stops, and then you get a brand new instance created. And as that's running, it sees the other foo function call, because it's the same code. That execution stops, and a new one gets created. Okay? Now, what just happened here after 3 foo function calls? Well, I ran out of space. My solution? Well, I could just like draw more space, I suppose, like that. And then say, okay, well, here we got another foo function call. And so we got another one, right? And we know that every time one of these little dots right here technically represents the cout statement, right? In fact, that's literally all there's other to it. So even though I put 3 dots, there's actually just one command, which is a cout. But yeah. So far we have 4 of these. So technically we have 4 ones printed, but it's not looking to stop anytime soon. Because after the 4 one gets called, or sorry, printed, you get the other foo call, and this goes on forever. However, now I keep saying the word in theory. Why? Because what just happened again? I just ran out of space again, right? Now, sure, I could keep expanding my little call stack, but think back to an actual computer. Where is this being stored again? In main memory. Is main memory infinite? Maybe in your computer in the future when you're watching this, if anybody's watching this in the future. But at least in 2022, we have a limit. my computer has a limit. It only has X amount of RAM in it. It's quite a bit of RAM, actually, not to gloat, but it's still limited. And as far as I know, that isn't going to change, at least in the near future, unless we do some weird, we somehow make infinite RAM, which seems very unlikely. So this is going to be an issue for our solution of being able to write one infinite. Because a loop, the ones we know so far, there's no real cost to running this code. Now, sure, you're spamming the terminal with ones, but like there's no actual cost to running the code. As long as you feed it electricity, it's not using extra RAM, it's not using extra processing power. It's just constantly doing its job, and we're all good to go. It's a different story with the function call solution that I'm doing here. Every time that it runs, it's adding a new context to our call stack. And it has to remember it because at some point it hopes to return and it needs to know where to return to. So this is the major downside to recursion. There's no free lunch with recursion as there is with looping. With recursion, every time you do a recursive call, which is when you're calling the same function that called you, or other variations of that, which I'll show you eventually, you're taking a little bit of extra space in memory. Now, it's minimal, especially if your function is rather simple like this one, but it's not zero. And if you know something about computers, even in 2022, is that they're pretty fast. If I do this, I'm going to run out of memory pretty much immediately after I start running it, because it's just, there's nothing to stop it. It's just going to make like non-stop function calls. And each one's going to take space, but because it's going so fast, it's going to fill up all my memory really quickly. And what happens then? Well, when I run out of memory, I can't make an additional function call. So does the program just stop? Well, yes, it'll stop, but it doesn't stop very elegantly. It just halts, and you're going to get probably some kind of segmentation fault or just some nasty error. We'll see it later when we start coding, but it won't end well because you're basically out of memory. Stack Overflow. So does that make recursion useless then? Should I just stick to looping? Not quite, because you don't really do infinite loops all the time. Like, could you? Well, I guess in theory, if like you have a program that you really just want to run forever, I suppose, like maybe you have you develop a service that you just want to always like be on. So it just kind of makes sense to just have an infinite loop that's always on. And in theory, you can unplug it to turn it off if you wanted to, but you just want to run it forever. So I guess in theory, yeah, you could like have a scenario where you could want to run things forever, but it's not the norm. Most of the time, you want things to finish at some point for the majority of the code that you write. Even in code that runs forever, there are parts of that code that terminate, right? Like you have a function call, it runs, like for example, say you have an email server that you just want to always have on, right? So you always want it to be checking to see if there's new emails. But if there's a new email, maybe you want to send it to a device. So you'll run a function that runs through that code, sends it to the device, and then comes back. And maybe within that code, even though the function call that says, hey, check if the message is delivered. And that could be looping a couple of times, but maybe you have a timer. If it fails after 10 tries, then it stops looping and comes back and gives an error, or maybe tries again in an hour because the device could be off or something, right? So just because you have infinite code doesn't mean that the entire code base is all infinite stuff. No. Even in that code, there are things that start and finish. So we know for sure that if we want something to reliably run forever, or at least for longer than a few seconds, really, like recursion is kind of out of the window. Does that weaken it and weaken its use? Not quite, because it's still very relevant to be able to use to repeat things. But you might be saying, hey, why do that when I have this perfectly nice and clean way of doing repetition? Why bother with this function call and asking it that like slows things down? And now I agree with you. Looping is actually much more efficient than recursion. No matter what people tell you, no matter what the recursion fans or lovers will tell you, recursion is not efficient, and it's for all intents and purposes, it's kind of bad for for efficiency. Does that mean you shouldn't learn it? No, of course not. Does that mean you're only learning it in case other people use it? No, you're going to be using it too. Especially, you saw me talking earlier about 302 data structures. Oh, you're definitely going to be using it there. You're going to become one with recursion in that class, which is why we want to get you going on that bandwagon. But why? Why would you want to use something that has limitations? Because if it runs too long, it crashes. And it's just kind of confusing and unnecessarily versus like a loop. Well, because as much as you've kind of been involved in programming and 135 and 202 and some assignments being weirder than the other ones, at the end of the day, what you've learned to do is take a real world concept and digitize that into a program, right? That's what programming is all about. Taking a real world idea and making it become true in a computer, right? You say to yourself, hey, I want to do a calculator. Cool. Go code one. You code it and it works and you're happy. Hey, I want to make a video game. I want to make like a first-person shooter or something. Great. Code one. Use Unity or Unreal so you don't like code from scratch, but you code it. You create what you want, right? That is your job. Your job is to take somebody's wishes, whether that be your own or others, and turn it into actionable, like actual software that can do it, right? You're just a translator for taking real world ideas and converting them into code that does what they want to do. So, one of the big things that you want to be able to do is to easily do that conversion from real world to the digital world, right? And a lot of the times it's not easy. That's why homework is not easy. That's why, in general, the software engineers get paid the big bucks. Because, unfortunately, the non-programmers will ask you for the weirdest, obscurest things without really thinking about how it's going to work. And you have to kind of decipher what they say and come up with something. And it's probably like an incomplete explanation sometimes. It can become quite a mess, actually. But ultimately, your job is to do that translation, right? Something as simple as saying, hey, I want you to build a program that can take apples and oranges and, sum the amount of them. And that's what they say to you. And so when you do the code, you're like, oh, I meant like sum either the apples or the oranges. But you said the word and. Yeah, but I meant or. Like even something as basic as like logic, you understand the difference between or and when it comes to logic. A lot of the times people confuse these words on like regular language, like regular people speaking English, right? They might say like, I want this and this when they really meant this or this. And that happens way more often than you think. It can be an issue. But anyways, not to get too sidetracked here. My idea that I'm trying to convey to you is that recursion has a place in actually making it easier to take real world knowledge or ideas and putting them in code. A lot of the times when somebody tells you to do something, it actually is more effort to try to convert their idea into a while loop or a for loop or something than it is to actually use recursion. If you want concrete examples, you're going to have to kind of wait until 302 to see like really good examples. We're going to just show you like toy examples. But if you want to look further than that, look at something like Quicksort or look at something like a tree traversal. These are things you're going to be coding in 302. I have videos on that. You can watch them. But those are pieces of code, particularly for me in 302. Like I love going over tree traversals because like the code to do them is like this much. And if you were trying to do that little code iteratively, it would be like blah. So this kind of answers the question about why recursion. Because sometimes It's the easiest way to be able to take an idea and put it into code. It just makes sense to do that. And it would be much, much harder to not use it. But there is, a cost to this in the terms of efficiency. If you really want something to be efficient in terms of space, that doesn't take a lot of space to run because of, recursion building up that stack, you eventually are going to have to sit down and, it'll be gruesome and nasty, but you're going to have to convert that code iteratively, and that'll probably be better for the long run. But for prototyping purposes or for simple programs, recursion, keeping it in a recursive mode just to make it easy to write is the way to go. Quicksort, like I said, is a great example of that, and it's one of the better sorting algorithms out there. And by better, I mean like fastest to sort. Timsort is allegedly better than Quicksort, which is a combination of merge and I believe selection sort. Might be merge and insertion. No, I think it's merge and selection. But still, Quicksort is up there. And maybe the reason why merge sort and selection combination is known as Timsort is chosen better is because it's not, like Quicksort is really recursive, whereas I believe merge sort, you don't really, it's very easy to not make it recursive. So I mean, that could be why, just from in general, running out of memory point of view. But there is actually a version of Quicksort that can sort without using recursion, which is known as lamp sort. And if I put you on a spot and I said, hey, you got to learn Quicksort or you got to learn lamp sort for tomorrow, and you got to code it for me, it would be 10 times easier to learn Quicksort than it would be to learn lamp sort. Because again, these are algorithms that it makes it easier to understand them and to code them if you keep them recursively. Okay? So, like I said, unfortunately, that's 302 level. And, I'm not going to get there now. So I'm going to give you basic examples, and I might not convince you between this and the next video that recursion actually has a place out there. But that's because I'm giving you easy examples to kind of get you into the feel of recursion. Do not underestimate recursion. It has its place. It is very useful to programmers, and you should very much familiarize yourself and be comfortable coding recursively and also reading other people's recursive code and understanding what it does. And by the way, languages like Python have mnemization, which allow you to kind of still use recursive code, but it doesn't actually run it doesn't always run recursively in the system. It uses dynamic programming. So there are ways around the whole call stack issue that can happen behind the scenes and still be able to write recursively. See, the fact that that even exists shows you that people have actually put effort into keeping things recursively rather than trying to make them iteratively, just because again, it does make your life easier. Now, I will warn you though, a lot of people, they want to look cool and they'll just write recursive code for the heck of it. That's not a good thing. I mean, it's good if you're just learning recursion to do as much as possible because, the more you practice, the better you are, just like anything else. But if you're actually writing real code and you're trying to do something, whether it be an interview or just a project, do recursion when you have to and don't put it where it doesn't belong. You're just going to make things inefficient at that point. And yeah, I'll leave it at that. Okay? So 39 minutes into the lecture, I mean, well, you did see an example of recursion in the food thing, but still, 39 minutes into the lecture, now I'm really going to show you the basics of recursion. And the reason why is you can watch other semesters. I don't really have tried this before, but I really wanted to kind of bring you here and say, hey, this is why this exists. Now we're going to learn it. Versus hey, this is recursion. This is how you do it. Good luck, have fun with it. And then you're just going to be like, oh, why? So hopefully I've answered the why before I've given you the data. And it gives you more motivation to actually be interested in this and learn it. Okay? But hey, all the motivation you need is that recursion is going to be your next exam, right? So you better learn it. So, yeah. Okay. So first, even though I kind of explained what recursion is, the first thing that I should tell you is, what is recursion? And the ongoing joke about that, I went way too far there. is that recursion is recursion. That's it. That's the definition of what is recursion. Recursion is recursion. Now, if you got the joke already, then that's good. You're already kind of getting closer to understanding recursion. If you didn't, then maybe you can revisit the joke at the end of the lectures on recursion. But let's just go ahead and write a little bit of a nicer explanation of recursion, if such a thing even exists. So I'm going to go ahead and take a shot at giving you a definition of recursion that doesn't involve the word recursion again, which is easier said than done. So I'm going to go ahead and say that recursion is the process of solving a problem by reducing it to a smaller version of itself. So in 135, they show you some algorithm basics, and they said, like, one of the ways that you solve problems is by the concept of divide and conquer, right? Which is that you take a large problem that's maybe difficult to approach, like, hey, code me Microsoft Word, like an alternative to that, like make open office for me. You're like, whoa, that's a big step up, right? Well, yeah, but you could definitely divide and conquer. You could start by saying, okay, I'm going to start by doing like maybe just some basic user interface program. I can just like open a window or not, right? And once I get that done, then I can focus on this. And somewhere in that list of different things you gotta do, maybe you do a spell checker. A spell checker can be tested and developed independently of the whole program of Open Office, Microsoft Word. And that's a much better way of being able to not just code, but also to test your code. Because trying to test everything at once, like developing an entire new game or an entire new program and never testing it at all and just expecting it to work on the first is it's extremely optimistic, I'll say. So yeah, I'll leave it at that. But you definitely want to test as you go. And so recursion, that same concept applies here. That you typically want to use it to sort of reduce the size of the problem you're dealing with by dealing with a small step that's going to slowly get you to the goal. Think of it like you're a miner, you know, like Nevada, known for like the mining, right? So you got a little miner, you got your pickaxe, and you know that there's gold deep in this cave, but you still got to mine like 2 feet of like rock before you get to the gold stash. So what do you do? Well, you go at it, right? You just hit it. You hit it with your pickaxe, and you're hoping to eventually get there before you gotta leave or something. You're slowly chipping away at the problem, right? A lot of the time, that's how recursion works. You slowly chip away at the problem, which each, recursive call or each time you go around, if it was a loop, you would say each iteration. I'm choosing my words carefully to not use the word iteration. Every time you hit it, you're working your problem by making it slightly smaller until you hit the gold. When you hit the gold, that means you're done. So you want to stop hitting with your pickaxe because you want your gold to be some thick piece, right? Because I think it's worth more than tiny little pieces. They can make like a statue or something. So that's going to be an important concept of recursion. It's not just to be able to go at it, but also to know when to stop, right? And so that brings us to sort of the different pieces of what recursion is, or more exactly what a recursive function is. So whenever you're dealing with recursion, you're going to be dealing with functions, right? As you saw by the example that I kind of led you with here. So I can split a recursive function into 3 main components. And before I write them to you, I'm just going to show them to you, okay? So my function here only really has 2 lines. And you might be saying like, whoa, you said 3 components. Shouldn't you have at least 3 lines? Well, yeah, because this is kind of a special version of recursion. Let me tell you what the components are. The components are something to keep going, to keep pickaxing, something to know when to stop, as in like I got to the gold, and the actual action of pickaxing. Okay? So you giving the command to pickaxe is the function call, but you actually doing the pickaxing is what gets you closer to your goal. So in this case, what you're doing to get you close to your goal is printing the 1. To continue repeating this, we call that the recursive case or recursive call. It's the actual function call to yourself. And then the base case, which is the third component, would be the one to stop. But in this case, this one's going forever, so that's why it's not there. Okay? So let me write them down and show you maybe another example. Okay? So the 3 components are, and you typically want to have one of each at least, but you'll see that there's some variations of this. Is you have your base case, and the base case component is basically when the recursion stops. In other words, it's all cool to think about theoretical stuff, but you know, at the end of the day, you can't just theoretically sell somebody a product. You have to give them the product, otherwise they're going to theoretically pay you. So you want to have your, whether it's your iterative code or your recursive code, you want it to stop, right? And so that's going to be your base case. When does the repetition or when does the recursion actually stop? Okay? That's the first component, and I would say it's one of the most important because it's useless for something to run if you can't stop it, really. It's like, hey, I built a plane, but I can't land. So do you want to test it? You're like, okay. Like, it can't land, as in like, should I just fly forever? You're like, well, I guess. I mean, maybe take a parachute. So, yeah, base case, kind of important. All right. The other one that's also important is the recursive case. The recursive case is actually pretty simple because that's what makes the function not just any function, but a recursive function. The fact that it's calling itself so that it can go on forever, right? If any of you have been to the California Adventure, there's the Spider-Man ride, and the robots are building themselves. Like they build a robot builds another, self-replicates, they call it. You can think of that as like recursion. So here's your self-replication. The function is able to make itself, to make more functions of itself until it takes over the world. Or in this case, takes over your memory and has a crash. So calling yourself. And finally, the third component is you could have a function that, you know, base case, it makes a function run like 10 times. And then you have the recursive case, which like makes you make sure that you actually get to call yourself 10 times. But it does nothing so far. So like, what's the point of the function, right? So you want to make sure the function actually does something that is getting you close to your goal. So maybe actually hits the rock in the pickaxe process to get you close to the gold. So I'm going to, I don't have a really technical name for that. So I'm just going to call it the do something. To get us closer to the goal. Or other than, goal, you could say like solution to our solution, or, to completing your process you're trying to do. So goal is kind of like a left to interpretation of what you're trying to do word. So yeah, this is the 3 major components or main components that a recursive function should have. And a recursive function is one that involves recursion, right? So we have the base case, which is basically how to stop the recursion once you've started it. The recursive case, which just means basically calling yourself, which is usually just the same function name as the function that you're creating. And finally, the function should actually do something to to make it have a purpose, whether that's C out of 1 or do some computation and so on. Okay, so let's go ahead and do a simple, we know how to do a bunch of things with while loops, so let's try to make some of those with recursion. The first one is, let's revisit our one example and say we want to print it out 10 times, okay? So let me copy paste. So we have our function foo. And we want a way to make it stop after it prints a certain amount of time. So we have the do something part, which is the cout. We have the recursive call. In fact, here, let me write a comment. So this is my recursive call. This is my do something to get us closer to our goal. I need my base case, which is how to stop it, right? But how do I stop it? Because remember, every time you make a function call, it makes a brand new instance. So if I make a variable anywhere in this function, you know, and maybe I set it to something, or I increase it each time, or whatever. Every time I do a new function, it's a new copy of the variable. So I can't really transfer information between function calls. They're all separate. Is there ways around that? There's 3 ways that I can think of. One way that you could communicate between different function calls is you could use a static variable, right? So static variables, remember, they're not just something you use with classes, but you just have normal static variables. In this case, this is a static variable that will persist the content between each function call. So there has to be some magic done with the call stack to actually be able to access this from any function call. This is actually a really cool way to keep track of how many times a function has been called, because all you gotta do is like, say like x++, and then every time you run this function, that static will increase. And then I guess at some point you want to print it out. But at some point it has to be within the function, right? But I guess this would be one way of solving it, but this isn't really like a purist way of solving recursion. So you don't really see it used, and I discourage you from doing it other than to learn it once and move on. Another even less like purist way of doing it is to use a global variable. So I could do a global variable, and then what I can do is I can just simply increase it each time that I'm running the function, right? And this actually kind of is reminiscent of like a while loop if you think about it, right? Like a while loop, you have your while loop code, and if you wanted to run X amount of times, you would just put a variable outside and then set it to 0, for example, and then every time you run it, like this literally looks like a while loop at this point, right? Because like, you know, I just increase it. In fact, let's do that actually. Let's stop this for a second and do the while loop version, just so we know. So remember, what I'm trying to do is print out I 10 times, right? So if obviously a for loop would be much easier, because you know, all I have to do for the for loop is just say like for int I equal to 0, I is less than 10, I plus plus, and then just say cout 1, right? So we know that like this would be a solution with a for loop, right? In fact, if you were allowed to use loops, I would say this would be the best way to do it. Yeah, for loop is a counting based loop, whereas a while loop is what you usually use for event based loop, right? Or condition based looping. So, right, that would be the nicest. But if we insisted upon using it with a while loop, I could make this an infinite loop, put my variable outside, and then do my something to get me closer to my goal, which you also do in the loop if you think about it. You always do something in the loop to make you actually get closer to what you want, right? The reason why you have the loop, right? However, that's, you know, all you really usually have, or in this case, because you want to be able to increase the counter, you need to find a way to stop this loop, right? So what do? Well, you can increase your counter with the I++, but then because you wanted to stop it for 10 times, you would put a condition, right? So that condition could be here as simple as saying, well, I is less than 10, right? And this would work fine. What would happen here is you start up with I equal being to 0. 0 is less than 10, so you would go into the loop. You would see out, the 1, and then I would become 1. And then it would run again and again and again until it gets to 10. And then when I is equal to 10, it would not enter the loop. And you would be done, right? But what if I said, hey, I don't want you to put that condition inside the while loop. Like, I'll let you use while loops, but you're only allowed to use infinite while loops. Like, why? I don't know. Just because I said so. So this is not allowed. So you have to use an infinite loop like this. What would you do if you still wanted this code to like function by running 10 times? You could use break statements, right? So you can go back and use a break statement. And remember, break and continue. Hopefully you do. If not, let's reboot really fast. So in a loop, you can halt a loop at any time by using a keyword known as break. So if I just put in the keyword break in here, when this code runs, it's going to run this, and then it's going to see the break, and it's immediately going to stop the loop and exit that nearest loop. Now, if this loop is inside another loop, it would just exit the nearest context loop. So like this inner loop, and the outside will still be running. So that's break. And then continue is kind of like an alternative to like, it's not the opposite per se, but what will happen with continue is anytime it sees it in the code, is going to immediately stop that current iteration of the loop and go back to the top. So this runs, and when it sees continue, it immediately goes back to the top of the loop and evaluates this condition again. And if it's still true, then it goes back in the loop, sees this, and stops it. So whereas with break, it just kicks it out of the loop, continue just brings it back to the top to check the condition. So in this case, it would never run this piece of code. So I would always increase by 1 each time that loop runs. Okay, so hopefully that refreshes break and continue. Now that it's been refreshed, we can see how we can use a break to actually terminate the loop after we print it enough times. How do we do that? With a condition, right? And how we do conditions in C++? If statements. So we can just bring in that condition from up here that we were checking before and just put it in an if statement. And then if it's true, that means we need to stop the loop. Or actually, that's incorrect. Because now we got to flip the logic, right? Because right now, if it's true, we keep going on the loop, right? Because if I is less than 10, then we keep going. That's what we would have put here. But now we actually need the opposite. We want it to stop when it evaluates as true. So what's one way we can do it? Well, I guess the really like ghetto way of doing it is I could just reverse it by that, putting a not symbol. So now whenever it's true, it's false, and whenever it's false, it's true. But it's like, oh, would that work with the 10 though? The 10 will be false, which becomes true. Yeah, no, that would work, yeah. But, it's kind of like a better way of doing it is just to change the logic for it. So I can say like, if I is greater than 9, or I could say greater than or equal to 10. Either one of those would work. And that would be like a much, much nicer way. Like, much better. It's like the meme, you're like, no. It's like, yeah, this way, right? So, yeah. That would be a much nicer way of putting it. But I suppose if you had some really complicated like if statement and you just wanted to bring it in down like this, slap it with 2 set of parentheses, put an exclamation point, and this bad boy is ready to go. So, yeah, you could do that too. Okay? And anyways, just in case you haven't figured, you just put a break in there when you're done, right? So, here we go. It ain't much, but it's honest work. We got ourselves a little loop system that will run and print 1 10 times and then break out, right? We could have done this all in this little for loop like that, but, it's a good exercise that we're doing it this way because it's actually kind of teaches us, like, think back to the recursion, the 3 concepts, right? Base case, recursive case, and your do something. We kind of have that here now. We have our do something here. Our recursive case is just a mere act of hitting this closing parentheses, because that will kick us up to the top and it's running forever. And then our base case, the way to stop it, is this right here. That's it. And it turns out that this is kind of how we're going to do the base case in recursion. So all I got to do is just copy and paste it here. Keep the plus, bring it up a little bit, and then bring that here. Now, we're almost done, but not quite, because guess what? Even though we have a base case now, it's never really gonna run, actually. And why is that? Well, I'm glad you asked. Because we have a recursive case before the base case, and you should never ever have your recursive call. I said case, sorry. You should never have your recursive call before your base case, because otherwise your base case is useless. The idea of the base case, the goal of it, is to stop the recursion. And the objective of the recursive call is to keep the recursion going. So you need to flip that around to check if you should stop the recursion before going ahead. It's like, imagine I'm teaching you to drive and I say, hey, when you get to a stoplight, check if the light is green or red. If it's green, keep going. If it's red, stop. If it's yellow, if you feel lucky and there's no cops around, you can floor it and maybe pass the light before it turns red. Or if you're feeling unsafe, maybe you should stop also. Okay? Well, let's forget about yellow for a minute. I'm not encouraging any unsafe behavior. Red or green. The first step of this is check the light. If it's green, keep going. If it's red, stop. Second step is if it's not red, then keep going, right? So if you see red, stop. If it's not red, keep going. If you flip the logic around and say keep going and then check the light, it's like you're gonna check the light. You're gonna check the light after you already ran that, which will work okay if it's green, but if it's red, then you're gonna be like, oh snap, I just ran a red light, and then your luck is it's gonna be there and the cop's gonna pull you over. So we need to check the light before we pass the actual stoplight. So in this case, we want to check if we've hit the base case to know that we have to stop before we try to do the recursive case again, or recursive call again. So in other words, this right here should always be after the check. If you're not doing like infinite stuff, which you really shouldn't be doing. Because like I said, in the real world, infinite is not very useful, particularly with recursion. It's definitely not useful. Okay, so we flipped it around now. So we've solved part of the issue, which is an ability to stop the code from going on forever, but we still have an impending issue per se. Now, this code will work as is now because we're using a global variable, right? We're using that int I equal to 0 on the top. So, and it also, this will only work once, because like, let's say your main code calls foo, starts out with a 0, it increases to 1. The word break isn't going to work anymore for us, right? Because it's not a loop. But we can easily replace that with something else. We can replace it with a return statement, right? Because return terminates a function early, right? Well, not early, it just terminates a function, right? You typically write return like if you're doing a value returning function, you do like return 5 or return x, right? When you're doing a void function, you typically don't write return unless you're doing some kind of check, like to see if something is invalid and then you return early. But you can do it. You can return anytime you want. You just put the word return and that's it. So we're going to take advantage of that. And in lieu of using break, because break wouldn't do anything for us here, we'll use return. So now looking at this again, we have foo, we have cout ones, we have I++, which both of these are technically getting us closer to our goal. We have the check here, which eventually, because of the ++, every time this function gets called, it'll get increased. And eventually it's going to hit 10 and stop. And then we have a recursive call. So this is going to keep going in circles here until it gets to 10, and then it's going to kick it out. And we're going to be all set to go, right? Yeah, but there's one problem with this. It's only going to work once. The next time you try to do this, like let's say you want to print I 20 times. So you call foo twice in main. First time it's going to print out 10, no problem. The second time though, it's going to be already 10, so it's just going to immediately return and just print out one instance of it. So how do we fix this? Well, we got to reset our variable, right? So if we're insistent upon using a global variable, I suppose what you could do is you could say I equal to 0 here. So you can reset I. So the next time you call foo, it's ready to go at 0, right? Another thing that I want to point out is that when we hit that return statement, it's not like it just ends immediately, right? Because like, let's think back for a second. Like let's say instead of 10, let's do like 3 or maybe 4, small number, okay? Think back to your call stack with this stuff. Here, let me actually copy and paste it down here, but shrink it. Here we go. Okay, so let's just say that instead of 10, it's going to be a, we'll do 4. I just want to make a small enough number that I don't run out of memory here. So the first time, we have our main, and somewhere in main, we have our function foo being called, right? So then we have our first foo call, and then let's just say the terminal is over here. So we get a 1 printed for the first cout. I becomes a 1, so let's just keep track of the I, which is technically up here, so like in the global context. So right now it's 0, so then it gets changed to 1, and then we see that I is not greater than 4, so none of this runs, and then we see a foo call, so then we have a second call, right? So let's just erase this comment, so we have space. So then this stops, and it gets halted right when it sees this line here, right? It sees this, and it gets halted there. So that's where it's going to remember to come back to. Okay? And then, it runs again, and it prints out another 1. I gets increased to 2 now. And then eventually it get the if statement check, does not evaluate to true, so it keeps going. Gets a foo call, so this program stops and builds another foo. Okay, so we get yet another foo being called here. Okay, this one's a main. Don't get confused because I put the word foo there, but foo in there. Okay, and then 2 is going to become a 3 now. Another 1's going to get printed out, and then 3 is still not greater than 4, so greater than or equal to 4. So we have yet again another call. Okay, so this is our 4th foo call. If you get a 1 printed, I gets increased to 4. Then to say I is greater than or equal to 4. Oh, it is. Finally, we're done. What's next? I gets reset to 0. And then after I gets reset to 0, we see a return. So with that return, we finish. We don't ever run this again. That's good. Otherwise, we would go forever. Not good. So when that happens, this is done. So we go back to the next one here, and we're back here. Now there's nothing beneath here. So this function itself is done. But technically, if there was code down here, so if I had like a cout 2 down here, then that would run. So we get actually a 2 printed out. After that, then we'd see these, so then we're really done with that. So this context would end, right? So that what I'm highlighting in is like being erased. Here, I'll just erase it to make life easy. Nah, I'll leave it in. Maybe what I'll do is I'll slash it. Okay? And then it goes back to the previous context, which is also pointing here but in this foo call. It sees another 2 in there, so it prints out the 2, and then it comes back to another context. So it's important that it remembers that the order of these things, especially if there's code after the function call. So now we're there, yet again, 1 more 2 gets printed out, and then this comes back, and now we're in main. So main continues and the program goes on. So important to note here, when it finally sees a return statement in the foo function call, it's just that specific instance that is done. It needs to go back to the other ones and continue where it left off. It is very possible, and it does happen often, that the recursive call may also have other function calls in it and other code after it, just like we're doing here. In fact, I'm going to explore this and tell you, when I tell you about head and tail recursion. But for now, I just wanted to point out that the functions don't just disappear. They're still there, and they still got to finish their code after they return from like the tail. That's the whole reason we have this massive call stack, because the program assumes that at some point we got to come back and finish this, because the program doesn't terminate until it sees that return 0 at the end of main, right? Unless you do like exit or something. However, before we go any further, let's revisit this global variable issue. So this works, yeah, and it's recursive, but it's not ideal. It's never ideal to use global variables. It's problematic. You could use the same logic I have here with the static solution. All you would have to do is bring that back in. So I could, here, I'll just copy paste it. So I could just as well do the following. I would say this is better solution, but not still the ideal one. So I could bring the static solution back in. And now this is all working, and at least it's self-contained within the function. You know, it's not going to mess with other people's code because there's no global scope. But still, again, it's not ideal way to do it, because pure recursion shouldn't have to rely on non-recursive stuff to be able to function. And by that I'm saying pure recursion, the recursion done right in a way, is self-reliant. The code is running and it doesn't need to rely on remembering other instances other than the information that's passed into that instance. Languages like Scheme, by the way, it's a programming language, don't even have loops. It's all about recursion like this, and the specific, there's different variations of Scheme, but like the more pure versions, they don't let you declare variables other than the ones that exist within the function itself and parameters. So the solution of static wouldn't really work, or globals for that reason. So what does that leave us with if we can't do the static solution and the global solution? Well, we're going to do the right solution per se, the one that you want to learn and the one you want to use. And what is that one going to be? Well, there's no one simple way, but the most popular way to do it is to use parameters or arguments. So just throw in some arguments in there and you're good to go. And voila. So now, when this gets called, yeah, you need to pass it an argument, sure. Pass it 0, or if it's a function call, maybe you can use like a default parameter. So you could like, you could do something like that if you want, so that it sets it to something initially. But once you're in here, you no longer have to do this nastiness here. And you don't even need to technically do this, the I++, because you could do that right on the function call itself. Because now the function call, you want to pass I, right? And if I put it like this, it'll work just fine. However, if I want to save one line of code, all I really got to do is just pass in I plus 1. And then I can get rid of the I++. Yeah, that's cleaner. Be careful though. Don't go in there and doing I++ like this, right? Because that shows you don't remember post and pre-increment. You could, however, do plus plus I. That would be fine. That would be acceptable. Just don't do I plus plus. You can do plus plus I or I plus 1, because I plus plus, what that expression returns is the old value of I before the increment of 1 added to it. Whereas plus plus I, post increment, I said I might have flipped them. This is post increment, the other one is pre increment. So post increment guarantees you that you get the value after the increase of 1, whereas pre increment gets you the old value. They do different things, so beware of that. So yeah. Anyhow, this now is a good recursive function. Congratulations on that. You've done it. Well done. We have a function. We have an argument in that function, the parameter there, that is passing in an I. And then every time this function gets called, it's going to refer to that parameter to see whether we have reached our goal. And then the next time you call the function, you send information that tells it where it's at, so that it knows if it will finish in the future or not. So it can see, if you pass it with a 5 and now it becomes a 6, it can see that it's getting closer, and then eventually when it gets to the goal, it's done, right? So very, very important. Okay. There's a lot more to cover with recursion. We're just getting started. We just finally completed our first recursive function that is like well done and clean. That has a base case at least, but there's a lot more to see. But we are at the 1 hour and 15 minute mark, so I'm gonna take a quick break on myself, and then I'm gonna record the next video. So you're more than welcome to check the next video immediately after, or to wait until the next class to check it out. So thank you all for watching, and I hope this was a nice introduction to recursion. We're not done by any means. You're going to see a lot more in the next video. So really, there should be one long video, but I want to take a quick break. So thank you all for watching. I hope this gets you closer to learning how recursion works and embracing the meta of recursion. So good luck, and I'll see you in the next one.